I know. Notes in the camera. I can't deny that I made a mistake. Like, I didn't say that. Let's rewind this a little bit.
You're fine, I will block
We are
it.
very happy to have Adam Sullivan here, and he is going to talk a little bit about structural equation models. He is a PhD candidate at Harvard University. Adam.
Larry said, I'm Adam. I'm excited to be here and talk with you. So with our program, we end up writing 3 publications that work towards our dissertation. So this is the first of my publications, and then I have 2 others that I'm working on right now. But this is dealing with linear structural equation modeling. It's heavily used in social sciences and economics. So what we did is we looked at it and we started looking at the assumptions that are made on the modeling, and we decided to come up with sensitivity analysis just to at least check one thing that one of the assumptions that are made. There's others out there, so there is more need for research on this, but we just are going to highlight one of these assumptions. So I'll talk a little bit about what structural equation models are, since I'm assuming most people haven't had any experience in them, or maybe haven't even seen any articles that use them. And then we'll talk a little bit about what confounding is and the bias of these effects. And then I'll get into the actual sensitivity analysis, talk a little bit about what these mean, how to use them, and then I want to just give an example. And the interesting thing that wasn't necessarily the aim of this paper that came up, we'll talk about, and that's kind of the scope of bias. So the effects that we care about is where we focused our bias on. However, these models are used because they define a whole large number of effects that aren't necessarily of interest to the researcher. And when we started looking at where does this bias go of the main effects that are cared about, we started finding that we were able to prove what effect is any effects that are always going to be biased. And sometimes these models lead to further research and further research funding, so it would be very important to know where other bias is present. So it ended up being a very interesting topic that wasn't what we set out to do. And then we'll just probably won't have too much time for this missing path analysis. So I'll conclude and then we can kind of talk about this or answer any questions you have. Feel free just to interrupt me if I'm moving too fast or something, or if you have a question on it. I'm pretty comfortable just stopping and answering a question. But you can also wait to the end and ask questions as well. But if you want clarification on something on the slide, just stop me while we're at the slide, and then we'll go on after that. Okay. So structural equation modeling, it's a big topic. Linear structural equation models are also widely used. They're a very specific type. And they're really used because they can model a whole number of paths and information at the same time. So rather than having to fit a bunch of separate models to analyze all these different features, structural equation models seek to analyze a whole complete structure at one time, a number of paths. And that's why it's the main reason that they're widely liked and widely used, because they take very complex relationships, they model them all at the same time. However, many of the times they leave variables out of these models. One of the key assumptions for a structural equation model is that you have every path or every relationship represented in it, and that you have every variable accounted for. When you leave one out, you violated one of the main assumptions. And so I'm sure you've learned in a lot of your classes, when you violate an assumption, you can't necessarily be sure that the answers or the results of your model are correct anymore. And this has kind of been ignored in the past with these. So our idea of this paper was to go in, look at a structural equation model, and I'm going to define what these direct, indirect, and total effects are. But those are the effects that researchers typically care about. And our idea was to see, are these effects, are they even present in a model when you have these missing variables, or where would missing variables in this model impact these 3 effects? Okay? And then we determine a proper way to test the sensitivity, which I'll talk through. And then after that, we wanted to know, where does this bias go? So it's got to go somewhere in the model. And so we explored where that happened. So a little bit of notation about how linear structural equation model is based a lot on graphs and path diagrams. So what they do is they have these rectangles in their models, and those represent observable variables. So those are variables that you can actually collect data on, or you have collected data on. Circles represent what we consider latent variables, and those are things you can't necessarily collect data on. If you look at, say, a person's attitude, you don't really know how to measure an attitude, but there's other variables that you can kind of get at to gauge a person's attitude. So you'd consider attitude itself to be a latent variable, something you can't necessarily observe or collect data on. Arrows represent what they define as causal relationships. So if you have, go to this diagram here, we would say that this latent variable has a causal impact on x1, also has a causal impact on x2, and the variable y. So x1, x2, y are all observable variables. That means we can collect data on them. They could be missing, though, from your data set, so it doesn't necessarily mean that somebody physically has collected data. They just have the ability to have data collected on them. This latent variable is some sort of relationship that impacts these three observable variables, but is not something that can necessarily be measured. Okay, and again, that's an easy example is something like attitude. What we're considering is what happens when you have some sort of unmeasured variable that has a causal impact on two other variables in the model. And that's something that we call a confounder. Okay, this variable here, this unmeasured variable, it's in red. It would be something that you would leave out of your model when you're doing your data analysis on. It's something you don't even consider. And it actually impacts this effect here. It could completely wipe that effect out. It could reverse the way that effect is seen. And that is why we want to look at these unmeasured confounders in this. Okay? So from this model, structural equation models, a lot of the programs that do this kind of thing, the researchers use this, aren't necessarily statisticians. So a lot of times they write this model out in computer software by drawing rectangles, circles, naming the variables. For these variables, they select items in their data set. For this one, they call it a name. The software essentially then takes linear equations off of each of these. So for y, if you noticed, we had two things impacting y. Again, this is unobserved, or it's a confounder that's not controlled for. So we have an error, and we have a latent variable. So the latent variable times its effect plus this error term is the linear equation for that one. So these structural equation models allow you to actually take this whole system and you have a system of equations at that same time. Okay? This has really strong assumptions. So it's one of the main assumptions of this is that our diagram is complete. That means there's no missing variables, no missing paths or relationships. Okay? The second one is that all variables in this model are normally distributed. This might seem reasonable if you're used to linear regression. However, in linear regression, the outcome variable needs to be normally distributed. All of the x's or all the covariates you put into a linear regression model do not necessarily need to be normal. In this model, every variable, no matter where it is in the pathway, has to be normal. And then all relationships are linear. So these are really strong assumptions. All we're doing today is we're addressing just this first assumption. Other assumptions need to be addressed more, and a lot of times this model the linear structural is not necessarily the one to use for most cases. It is widely used, and that's the reason we're creating this sensitivity analysis, because it's used, it's out there. Psychologists, sociologists are using this. So we want to at least develop a tool to test this right here. So what we did is, in mediation analysis theory, or causal inference, A represents some sort of exposure or treatment that you're assigned to. M is a mediating value, and Y is your outcome. So these are just random covariates that also could be included in there, sometimes baseline effects, age, sex, race, whatever kind of covariates you might have in your model. So what I did is, I took this unmeasured confounder and I kind of moved it to any of these relationships or any of these paths in there. And I wanted to see which of it impacts this direct, indirect, and total effect. So we do this kind check for identifiability. And identifiability means that I can consistently estimate a correct, I consistently can estimate an effect. Okay, so when I have this identified, I can then take my statistical software. I can even take you could actually do a lot of this out with matrices, and you can actively find a numerical value for an effect estimate. If it's not identified, you aren't going to be able to do that. You are possibly going to end up with an infinite number of solutions that will work. So we check for identifiability, and we consider the scenarios that we consider in this paper only where these direct, indirect, and total effect are biased. So before I go on, I want to explain a little bit about what this direct, indirect, and total effect are, since most of you probably haven't seen it. So a direct effect, usually the example I use to talk about mediation analysis is, it came out of, say, smoking. When you look at smoking cigarettes, they've shown research that it causes lung cancer. Does smoking cigarettes cause lung cancer? So here's smoking cigarettes, lung cancer. Does it cause lung cancer directly? Is there just a relationship where you smoke and you get lung cancer? There's no other biological pathway, it's just purely it causes cancer itself to happen. The other way to consider it is to say, does smoking cause some sort of gene breakdown or some sort of genetic genes that possibly turn on, and those genes are what causes cancer? And so mediation analysis seeks to figure out how much of this effect from smoking on lung cancer is just from the cigarettes itself, and there's nothing else in this pathway, and how much of it is mediated through, say, genetics or through some other relationship. So this direct effect is just this arrow that goes directly from your exposure to your outcome, and your indirect effect, your indirect relationship, goes from your exposure causes something else to happen or has a change on something else, and that change is what changes or affects your outcome. Okay? The total effect is the combination of this, because sometimes you don't necessarily care about how smoking causes lung cancer, you just care about how much of a risk does smoking have on lung cancer. I don't care if it went through the genetics, or I don't care if just it immediately affected lung cancer cells and caused them to multiply. And that would be the total effect. And the total effect is actually just the sum of this direct effect plus this indirect effect. Okay? So it's a very simple mediator model. There are multiple mediator models. I'm working on a paper right now that actually does longitudinal mediation. So this would be just a one-time point model. So we care about these because typically when a researcher is seeking something out, their real question has to do with one exposure, one outcome, and possibly some mediators in the center. Now they include a lot of other covariates in there, and structural equation models will estimate all these other covariate effects, but they hypothesize typically with one sort of direct or indirect. There could be a number of these little diagrams within their model that they care about. So we just want to find out where would the confounder be that would impact the direct, indirect, and total effect in these models. Okay. So when we did that, look at the total effects first. And so this left arrow has to deal with where the leftmost arrow of the confounder was. So if I go back, and remember the confounder, so this would be the leftmost arrow of the confounder, the rightmost. So it looks at where this confounder impacts. And if the confounder has a left arrow that's pre-exposure, so something that happens before we even start our study or before the person is exposed to something, it doesn't impact the results at all. So they can have an unmeasured variable with a left arrow into the pre-exposure, doesn't change anything. There's no bias in the model, doesn't impact the results. However, if there's a left arrow on the exposure, and the right arrow is on the mediator or the outcome, the total effect would be biased in those two situations. So for the total effect, it's only biased, and we call this exposure, we call it exposure mediator confounding and exposure outcome confounding. Yes?
Could you have confounders with more than 2 arrows, like 3 or 4, and then how would you deal with those?
You could have those, and those actually get really complex to deal with in sensitivity analyses, and there currently aren't any sensitivity analyses dealing with those right now. So the ones we kind of deal with, what we usually would suggest in this case is, if it was, for example, if what you're asking is, if you had one that had arrows into all of these,
Right.
you would probably deal with it as exposure mediator confounding, and then you would also do a separate analysis to look at it as mediator outcome confounding. And that would be how you have to deal with it. In the future, hopefully somebody will come up with more. I think they could come up with it, but usually what they find is once you start to complicate the confounding and the sensitivity analyses, you end up getting really complicated mathematical formulas, and researchers won't use them. So what we do is try to keep it very simplified so that any level of mathematics that somebody could possibly implement this and use it. But it's a really good question, and unfortunately right now, the only way to deal with it is to break it down separately and to treat that as an exposure mediator as well as a mediator outcome confounding.
Okay.
So the direct and indirect effects, we find a very similar situation. For the exposure mediator confounder, the direct effect is not biased, but the indirect is. For exposure outcome confounding, the indirect effect is non-biased or unbiased, and the direct effect is. So these are the effects that you can, so both effects are identifiable if it's, again, pre-exposure confounder. Once it's exposure mediator, only the direct effect is identifiable. Exposure outcome, only the indirect. And mediator outcome, and neither the indirect or the direct effect are identifiable in that case. So those are the three situations we deal with. If you remember from the total effect, it was exposure mediator, exposure outcome. And then for this one, it added in mediator outcome. So those are the three scenarios that we're actually interested in. And those are what we focus on. If you end up having multiple mediators or different mediators, what you would have to do is this type of sensitivity analysis on various parts of your graph. And that currently is the best utility to do this. If you ended up finding that that wasn't very enticing to you, or you didn't like having to do that, this probably, the suggestion at that point would be to have this researcher use a completely different model. So what we're trying to do is, again, build tools that these researchers who are using these models can use to help understand their work a little better, and it also can be used to test their work. Instead of just saying, well, you left this variable out, it could impact it, and we are going to test for that. Okay. So exposure mediator confounding. What happens here, the reason there's bias present here is this exposure and this mediator are associated because of this unmeasured confounder. So if this arrow was not here at all, so there should be the zero effect, let's say, for your exposure mediator, your software or your statistical tools would give you an effect for this because of this unmeasured relationship here. Okay, so what we want to do is try to figure out a way to test to see this effect estimate that you have, is that truly because there's an effect present, or is that purely because this unmeasured confounder associated these two variables and I'm seeing some sort of estimate in there? Okay. And the total effect is, again, biased. The reason the total effect is because, remember, the total effect is when you add up this direct and indirect relationship. Well, technically, you could have this arrow missing, so you could have no direct path, and you could have no path from the exposure to the mediator. However, you would have a path for a total effect to still be there. So you could have an exposure that's not even related to the outcome, but the mediator is, and you would still find effects, statistically significant effects, possibly in your models because of this. Okay. Exposure outcome is the same way. The total effect is biased, again, because you might not even have these two arrows here, but you have a relationship possibly, or an association that is showing up. And the direct effect is biased there. And the interesting scenario that we decided to use, I'm going to use today just to kind of walk through how we did the sensitivity on just this one. And then I have a data example for this one. So we're focusing on this one because that's what I have the data example on in our paper. So both the direct and indirect relationships are biased in this one. And the reason for that is when you try to identify this direct effect, you actually condition on the mediator. When you condition on this mediator, you set this to some sort of specific value. When you set it to a value, it no longer has any kind of variation that affects the outcome. So there should be no relationship between these two. However, there's a causal inference that's called DAG theory. This is directed acyclic graphs. And it's been shown mathematically that when you condition on something that's what's called a collider, where these two arrows go into it, you actually open up a relationship here. So this time you now condition on this to try to find your direct effect, and you end up opening up a path that allows the direct effect to seem to be there when it might not be there. Okay? So the direct effect and the indirect effect. The reason the indirect effect is, again, this arrow might not even be present in the model. So there might not be any impact of the mediator on the outcome. Okay. So we know that confounding affects this mediator-outcome relationship. So we want to first of all try to quantify the bias that's present here. And I want to try to correct for that. So that's basically the two steps of sensitivity analyses. Whenever you do any kind of sensitivity analyses, what you try to do is you try to identify some sort of bias that's present. How much either overestimated is this effect, how much underestimated is it, and then you try to find a way to actually correct for that. So we need some assumptions to do that correction. Okay. So we need that this direct effect of U is the same for all levels of A. And what that means is, if my unmeasured confounder is here, I don't want there to be some sort of interaction of this exposure and this confounder here. I don't want my confounder to act differently depending on a person's exposure level or medication level that they've been given. If it's a randomized trial, I don't want the unmeasured confounder to act completely different in a person who doesn't have a treatment versus a person who does. So I need that interaction to not be present. Okay. And then I need that the expected value of this unmeasured confounder is additive in A and M and C. And so what that means is I need that I can find the expectation for this unmeasured confounder, and I can find it as some function of the exposure values plus some other function of the mediator and the covariates. Okay? So those are the two assumptions I need to have made. And they end up being assumptions that are pretty widely used in most causal inference sensitivity analyses. So we'll talk about how to define those in terms of what they mean when we get to actual data, the data analysis. I can show you how we kind of interpret what those are. Okay? If these assumptions hold, I end up with the additive bias, which means the bias we can identify, or we can set some limits on these values that I'll talk about. And then the bias is simply an additive component to this. So if we subtract the bias away, we have corrected for this bias. What they are is this, we have this delta, so the bias can be defined as this delta and gamma. So delta is the difference in the mean value of U conditional on M between levels of A. So when we condition on M, so we condition on this value here, and that delta refers to what is the difference. What is the difference in the mean value of that U when you do this? And again, I'm going to explain that much better when we get to this data example. So I'll be able to actually show you what that value means in a data set, or what it means for our example. It's a little easier to see that way. And then gamma is the direct effect of U on the outcome Y through M. And what that means is, back to our graph here, delta, or sorry, gamma is just this relationship of u on y from this arrow here. Directly meaning that it's not what goes through m. So you just want to know an estimate of what this effect is, how that would impact it. Okay. And then that is the added bias that's added onto this. So to correct for the bias, we would actually subtract that. The issue with this is we don't necessarily have some sort of known or true delta gamma value. Okay? We have to specify these. Okay? So there's not really anything we can go to and say, oh, I now know the exact true value of delta gamma, I can subtract the exact bias, and now I know the results of this. So we specify them, and we typically try to specify a range. So when you start a sensitivity analysis, usually what you try to do is you try to zero out the effect. What kind of estimates or what kind of values for this delta gamma would it take to just make it so there was no effect at all? Sometimes you find that that can be easily done with very small values, and that means possibly the effect that's there really shouldn't be, there really isn't a value there. Other times you see that you need an effect of like size 25 when in that field all effect sizes are below 1. And so if you need an effect of size 25 to wipe out an effect, that says that effect's pretty strong and your confounding didn't really impact it. So we try to specify a range of values that we think are acceptable. So the first thing you typically do is you try to find out what it takes to just wipe out the effect in general. So what kind of bias would it take so that when I subtract that bias, my relationship's gone. From that, you can learn a lot. You can say, wow, that took an awful lot. It took really large effects. My delta and my gamma had to be really big to wipe that effect out. And that can say your results are pretty solid. There obviously is some bias in there, but it's not enough to completely erase the effect. So then what you would go ahead and do is you try to specify a reasonable range of values. And when I say reasonable, it really depends on the study that you're doing and how other variables in the model tend to have relationships that impact it. And so we suggest that you try to pick values that are similar to the other values that are in the model. And I'll explain what that means when we get to this example. So remember, before I mentioned this total effect is the direct effect plus the indirect effect. So if you corrected the direct effects bias, which we just mentioned, that was just what we were talking about before. So the indirect effect has the same bias, it's just that its magnitude is in the different direction. So we take that bias that we found, or we specified values for, we subtract it from the direct effect to correct that. To correct the indirect effect, we actually add that same bias back to it. And again, what we do is, because we're specifying a range for this, we would subtract both of these values from our direct effect to have a range of corrected values, you could call them, for your direct effect. In this case, we would add that range of values, and we'd have some sort of what you refer to as a corrected indirect effect as well. So essentially, when you identify unmeasured confounding, you're able to make those assumptions. You end up being able to specify just two values. And from specifying those two values and a range of those two values, you're able to test the sensitivity of both the direct and the indirect effects in this case. And it's a very similar setup with the exposure mediator and exposure outcome confounding. Okay. So once this bias has been corrected for, we can kind of talk about what happens. What do we do with sensitivity analyses? Well, sometimes when you correct for it, the range of values that you've corrected for contain a 0. Okay? If they contain 0, it's possible that your effect wasn't there, because we just said we specified what we considered reasonable ranges for bias. If 0 is contained in that subtraction of correcting for the bias, it's possible that 0 is the actual effect. And with that case, we would say that this is probably not something that you should take a lot of weight in. This is not something that you should be publishing, or this is not something that should be put out there for people to read. And if you pick up the New York Times or other research journals, anytime something's published in the New England Journal of Medicine, and it's about something like obesity or cancer or smoking, it makes it to all the media. So as soon as you get a study out there, before anybody's had a chance to verify this study, the results are already out in the media. People are already possibly trying to change their lifestyle or making choices based on this. So if you had some study like that which came out, your range of effects contained 0, your whole premise that you published on might actually not exist, might not be there. What it means is possibly a researcher we'd hope that a researcher would see this and maybe at least try to collect data on the confounders and redo this study. The other thing we would hope is that if this research was published like this, somebody else ran the sensitivity analysis on it and was able to easily show that their effects were out there, that they could submit a call to retract a paper like this, because again, in medical and social and psychological research, people rely heavily on what they read in journal articles. They view it as scientists did a really specific procedure and they didn't make any mistakes and they did this right. The other thing that can happen is that the range of effects that you have are in the same direction as theirs. So let's say you have a positive effect and your range of values are still positive and they don't contain 0. So that means that possibly you have that same effect there. It might be a little bit smaller, or maybe it's even larger than what you noticed before. But that effect is still there. So scenario number 2 says your results they're still adequate or they're still correct. You just might not be able to still know how big of an impact this has. But you could at least know that, say, smoking does have some sort of impact on something. Or in psychological research, this drug that you're giving a person does have an impact on some sort of maybe attention or some sort of anxiety disorder. Maybe you don't know exactly, you can't quantify exactly how much that effect is, but you know that it's in the same direction because the bias correction did not zero it out and it didn't do what number 3 is, which is the opposite direction. When it changes the opposite direction, that means that the bias possibly allowed you to see something as being a healthy result when it possibly was a negative result in actuality. So the bias was large enough to have changed the direction of something. It also could be the opposite, something you tell people is a negative thing to do, something they shouldn't be doing. When corrected for, you find out, no, I was wrong, that's actually healthy, that's actually something that's positive for you. Okay? So scenarios 1 and 3 suggest that you would need to do more research, or your results are not necessarily valid in what you're trying to do. Situation 2 would say that you need to have a discussion in your paper or in your research to let somebody know that the effects you found are not necessarily something that's set in stone. This relationship between this treatment does not cause a 32% decrease in anxiety. It causes a decrease in anxiety. We just don't know how much of a decrease. The other 2 would say it causes an increase in anxiety, or it doesn't change your anxiety at all. So you don't want to give somebody a drug that does nothing, because there's a whole bunch of other side effects that it does negatively have an impact on. And you don't want to give somebody a drug that actually causes their problem to become worse. And so that's, again, those are what the 3 things you can find when you do these sensitivity analyses. So my example was looking at relationship between age and working memory. Okay? So we know that as you get older, that your memory starts to decline. And so this study was looking at this kind of relationship between age and memory. And so essentially they have people from 50 up into their mid-80s in this study. Okay? And the person who originally published this paper used a pretty complicated model. And another researcher came along and said, instead of measuring all these kind of things separately, there's an easier model that can be used. And this is something called common factor G, which is what psychologists use to kind of determine a person's working memory. And it comes from a score, so it's a latent variable, something you can't just calculate. But we typically use somebody's speed, flexibility, working memory, and all this fluid intelligence. And we use it to get an overall gauge of how their mind is working. Okay? So another researcher, Penke and Deary, suggested that this is the more appropriate model for social sciences. They published it, this is what was getting used. And so what they did is they looked at, does age just cause a decrease in a person's memory? Or does an age impact part of their brain, and that causes an impact on working memory? Does it cause some sort of deterioration? And so they looked at DTI, mean diffusivity, to check out certain levels of brain activity. And I suggested that maybe there's some sort of missing variable between the results of DTI mean diffusivity and this working intelligence. So the results were that the effective age is negative, so your memory decreases as you get older. As most of you are young here, you start to get older, you start to realize that even your mind will start to either forget things or it starts to decrease in ability. So hopefully that's why you start education, you keep on doing it when you're younger. I can tell you that starting your PhD at 27 or 28 puts you at a much different place than a 20-year-old that's starting it with you. I say that from pure experience and nothing to do with this topic, but you'll notice that your mind decreases as you get older. Okay? And then there's also a relationship between how age impacts this section. I'm sorry, it was not decay, but plaque or substances on the brain. So I suggested, actually sorry, there's the direct effect, indirect effect, and total effect from their model. And I suggested this unmeasured confounder, maybe it's sex. Maybe there's a different relationship in how these variables are for men and women, causing them to have some sort of different values of brain activity, or what we consider, because remember, we're considering this common factor to be how we're gauging somebody's memory or their ability, but it's a latent variable, so it's something we can't necessarily just give a test for that one specific thing. So maybe there's a different relationship between this memory in men and women, and maybe there's a difference in the way the brain appears for men and women. And this is, the reason I suggested this is because this relationship here is kind of disputed in psychological research, and this relationship is also disputed. So there are people out there that say those relationships exist, there are people that say they don't, and so I said, well, what if we just did a sensitivity analysis on this model? Let's say we assume that those relationships are there, we assume that sex is an unmeasured confounder, it's not controlled for in this study, and let's see, does it have an impact? Okay. So we talked before about this delta and gamma, and I promised that I would give you a little bit better understanding of what they mean. So in this, when I mentioned before that we have to conditioning on M, so what that means is we just look at it, we say we fix M to some sort of value, the mediator. So we want some sort of constant mediator. And so what this delta becomes is the difference in prevalence between two ages which are one standard deviation apart. So it's important to know your standard deviation in this. But again, age is the exposure on this. And so what we need is two people that have the same DTI mean diffusivity levels. So you just need they need to have those same levels, so you fix those. And then what you want to look at is what is the difference in prevalence between two ages that are one standard deviation apart. So that really depends on the data set, how wide of a range your values are for your data. And delta, again, gamma is the much easier one. That's just that, what's that effect of U on the outcome? And in this case, what is the effect of U on the G factor? So again, these are things we don't necessarily know. I don't have a handbook, or there's not a researcher I can call up and say, what are the values for this? This makes, do you have an idea of what the effect would be on this? They don't. Nobody would. So what we want to do is we want to start specifying these. And so one first step might be to try to zero it out. So we'll just talk a little bit about one of the things. Let's try. So if the difference in prevalence of U at some sort of fixed M with ages that are 1 standard deviation apart was 0.13. And the corresponding gamma of this was -5. This would lead to a bias that was the same magnitude as the direct effect, but the opposite direction. So this is what it would take to zero it out. So essentially, I need something that has an impact of 5 standard deviations in order to change it. Okay? If you've learned a lot about like the normal distribution, which I'm assuming you have, 5 standard deviations out is something that has a really, 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 really tiny probability of ever happening. So we can say that this direct effect of age is pretty strong. It seems reasonable that age causes a change in your memory. Okay? It would take a very large value, again, something of the magnitude of 5 standard deviations away from your mean to change that. Okay? What that says is that there is probably some sort of effect of age on this, and then we want to try to identify reasonable values for these, more reasonable. All right, so we define more reasonable. We could also eliminate the same effect by if you had 0.26 for your delta, but you'd still need 2.5 standard deviations away from it. And that's a pretty large effect for these. Okay, so 5 standard deviations, 2.5 standard deviations. It's not likely that you're going to erase this effect of age. Okay. So we consider the indirect effect now. Okay, so that's what we're just trying to zero out these effects here. So a difference in prevalent of 0.05, so just a 5% difference. You know, before we considered, say, a 13% or a 26% difference in prevalence. Now we're just saying maybe there's a difference of patients, a 5% difference in patients between men and women here. We would need something that was only 0.15 standard deviations away to erase the indirect effect. Okay, 0.15 standard deviations away is something that we would seem reasonably able to happen with a value. Okay. And remember, I'll go back to this diagram. This gamma is just this effect of this value on this common factor G. And 0.15 is actually smaller than 2 of the other relationships already in the model. It's actually smaller than a lot of the relationships. So having that relationship is already much smaller than what is already in the model, and it's reasonable to assume that something could be 0.15 standard deviations away. And a 5% difference at a different age level is really not that big of a difference between groups of people. Okay. So what you can show with this is that possibly this direct effect, this direct relationship of age on memory, it's pretty solid. It would take something that was uncomprehendibly far away from our mean to change it. However, this direct effect, or the indirect effect is possibly something that could be changed. So it appears that this relationship that they were trying to discover in the research, the relationship between age and memory has been known. It's been shown in a lot of research. Their new research, or their new indirect path, is probably something that can be easily wiped out based on whatever variable you chose there. I suggested that sex is a confounder there. There's actually a possibility of a lot of other confounders there as well. So that model you saw is the actual model that they put the data into and control for it. So there's nothing else. They didn't control for race. They didn't control for anything else. They didn't control for education level. So there's a lot of things we could think about that could be in that confounding there. So once you consider all those other confounders adding up with their bias in there, it's very reasonable to assume that this indirect effect isn't existent. However, it would take a large amount of bias to make the direct effect of age on memory go away. Okay. And then, so what I did, the next step is I just suggested to researchers for how to look through the values maybe in the model, how to look through values in the research for what types of effects are typically seen in these kind of situations in order to go ahead and kind of give us more of a corrected range of effects. And what we end up finding is when you have a corrected range of effects, the indirect effect actually changes direction from it. Okay, it changes direction from what they had the indirect effect being to in the model. However, the direct effect remains relatively unchanged. Remember, it's 0.65, so when you have the reasonable values in here, it's very similar in that. So again, the researcher would be able to say that the direct effect is, there's obviously an effect on age still. Sensitivity analysis didn't, you wipe that out, it didn't change that. It's just we might not know the exact value of that effect in this data set. Okay. So what we wanted to do is, we talked about just the bias of these direct, indirect, and total effects. But in these models, there's a large number of relationships out there. So what other effects are biased? These models are used because people have multiple mediators, multiple exposures, multiple outcomes, large numbers of observable variables and latent variables all put into one model. So there has to be bias that's spread throughout this model to account for the bias that we saw with just the direct, indirect, and total effects. So we wanted to kind of look at where that would go. So we developed a simulation to do this first. Once we found it, we actually went ahead and proved why it would be there. But we did the simulation because we weren't sure where the bias would show up. It showed up in the same exact place each time, and we actually went through and did a proof on that to show why everything else would be biased in there. Okay. So we just basically took all of our covariates as well as our unmeasured confounder. They're all normally distributed with mean 0, standard deviation 1. We've simulated 20,000 values for those. And then we set these, these are a moderate effect level in this type of situation is 0.6. And so we set all the paths in these models to 0.6. But we actually said that this value of C has no impact on the outcome whatsoever. That has a value of 0. But we wanted to see what would happen when we ran a standard model. So we know that the exposure is only accounted for due to this covariates plus some sort of error. Okay? The mediator is due to the covariates plus the exposure plus the unmeasured confounder that's not going to be controlled for in the analyses. And the outcome is not affected by the covariates because we erased that relationship there. And we have it affected by the exposure, the mediator, and that unmeasured variable plus some sort of error that's in there. And so we wanted to see what would happen when we did this. What we found is when I left this C to Y in the model, so I left this relationship in the model saying this relationship exists in the model. And remember, I set all these values to 0.6. So this one got 0.59 with a range of 0.58 to 0.61. So 95% confidence interval contains what it is. Same thing for all these three. However, this one was set to 0, but I found a statistically significant negative 0.17 for the relationship of the covariates on the outcome. I found that instead of being 0.6 for the relationship of the exposure on the outcome, it dropped down to 0.44, and I found that the mediator on the outcome also had a change in effect. Now these are two that we know about because this is something we discuss when we're talking about these direct effects and indirect effects of bias. What we didn't realize would happen is that any other value that goes into the outcome would also be affected. So essentially what we found is that when you have one of these models, you take the rightmost variable. So when you're looking at mediator outcome confounding, any other estimate that tries to estimate its relationship on that outcome where that rightmost arrow is, all of those effects would contain bias. Okay? If you have exposure mediator confounding, the rightmost arrow is on the mediator. and any relationship of any other variable that has a path that goes into the mediator will be biased as well. And again, this is important to know, and this is something we didn't actually think we'd be able to find or see. And so we actually went ahead and, I went ahead and, I say we, but I went ahead and proved this. My advisor looks it over after that. But I went ahead and proved this. And so it's something very interesting in this, because a lot of times from these models, other researchers can take a paper that's been published on this and say, well, if you notice in this person's model, they had these effects here, and I want to explore more about this relationship here. So they can actually possibly receive grant funding or research money to try to do a study to impact another type of relationship in this model, which was completely biased due to some sort of unmeasured confounder not being accounted for. And this was something we put in for researchers about what happens if certain arrows just don't exist in your data set. How does it change the bias of those effects? So we kind of talked about these 3 different scenarios. I talked about how to quantify just the sensitivity of the bias on just this third one, just because that was, again, the one that we chose to do a data example on. And then we kind of showed another interesting thing that we found out of this paper. There's a lot of these kind of sensitivity papers that are published out there, but we didn't actually think that we'd find some sort of actual set relationship between where the rest of the bias was. So we kind of think that's more of the novel impact of the paper, even though the sensitivity analysis is what led us to find it. And then the last thing we talked about in the paper is just about if there are certain relationships that are moved from your data, do you still need to try to do the sensitivity analysis, or can you just not have to worry about it? And so I want to thank you all. I realize we moved through a lot of stuff, sensitivity analyses, structural equation models, bias, causal inference possibly, and mediation, things you might not have seen. So I want to thank you for that. And do you have any questions that I can help with?
I guess not necessarily about the mathematics in general, but it seems like a lot of the purpose of your research is to educate other researchers about how to properly research. But in terms of actually making sure that people are reading this kind of things you're doing and actually implementing these kinds of more accurate, more correct procedures, I mean, I guess how do you go about doing that?
How do we go about doing that? And one of the things is you can start looking at, like, for example, if there was like some sort of psychology group that met, like we have joint statistical meetings that we met in Boston last year where statisticians from all over the country get together. So if you could go to a place, if you knew it was psychologists that were using linear structural equation models, you could give a talk at one of their national conferences, then you could possibly impact a large number of people. The other way to do it is to the best way would be to try to encourage universities who are putting out people with PhDs in psychology that are starting to do psychology research and social science research to start trying to encourage them to give their students more of a statistical background, or encourage policy change so that any kind of policy that's made due to psychological models includes somebody like a statistician in on the study design and in on the research that's being done. That's actually something in biostatistics what the FDA was having is large numbers of drugs were making it through all 4 phases of clinical trials. They were being put on the market, and then they were finding that they were killing groups of people. And these are very dangerous to happen, but they made it through all the process. And what they found is that there were times where there were incorrect statistical procedures followed either in the design or the analysis of this. So the FDA mandated that anytime you do a large clinical trial like this, especially like a phase 3, that you have to have a PhD biostatistician or a PhD statistician on that study from start to finish. And so that's one way that world has done it. And so it would be nice to see that the world of psychology research would start to move towards having people who are qualified to analyze quantitative data start to do something similar. But I know in the FDA that's one way they mandated that some of these changes take place by having a statistician on. gives you a lot of pressure as a statistician, realizing that that's your duty on it, is to make sure people are safe. And make sure that a company isn't hiding results so they can make a large money on their drug. Yes?
On a causal level, if we think about the examples, say, of age and working memory, surely every biological process, every behavior, everything that a person does has extraordinarily complicated biological interactions that result in the final symptom. Or if you're talking about smoking and cancer, the same thing has to be true. So how do you justify the search for intermediary causation when clearly there just must be so much more that could never be found or documented?
Okay, it's a very good question. It's kind of why you're really asking kind of why we do mediation analysis in general. Because
Right.
All right, the reason for that is a lot of times we can't actually impact the behavior. Maybe we can't change something that happens. For example, if your exposure was something that has to do with a genetic, some sort of genetic thing, we can't change that on a person. We can't ever physically manipulate their genes to change that exposure. If we knew that a significant amount of that exposure's effect went through some other cell, or maybe it was a protein deficiency, that it impacted the way this type of protein was made, and that protein is what really caused a relationship. That would lend for a biologist or somebody or a chemist maybe to create something that would either help increase that level of protein in a person, or maybe it would try to block that protein increase. So you can't necessarily make a change on that person's genetics, but maybe one of those intermediate things along the pathway, maybe you can make a change that changes that value.
So it's very important to have some kind of subject matter knowledge that allows you to identify what those causal processes may be.
Yes, and these are not, like, I would never try to undertake mediation analysis myself as a statistician. I would need to collaborate with somebody else. I would be the person bringing in the statistical knowledge and the modeling behind that, but I would need a researcher who truly understands more of the biological pathways or what other relationships could be impacting this to check for that.
Okay, thank you.
So it's highly collaborative when you're doing this work.
Let's get one more quick question. Let me check real quick. Jinping, is there a class after that meets in here? So make it a real quick one, Greg, and then we'll wind up.
I don't want to put you on the spot to do a whole group or anything, but it seems like you have it narrowed down to a couple cases where the effects really matter and the structure is pretty well set and it's all linear. Is that basically what was it that allowed you to prove that all of the biases went to very specific places? If you could just give me maybe a kernel, because that was very a cool result that it always went to that one specific spot.
Okay, so the reason for that, again, it has to do with, if I have this variable C, in my model I said C had no direct relationship on Y, but we found one that was there, okay? So this arrow is gone, shouldn't be there at all, from C to the outcome shouldn't be there. However, C had a relationship on A, which has a relationship on M. When I try to do that direct effect of the associated this exposure on the outcome, I actually can open up a relationship. So through these variables, you can have a relationship come down and go through there. And essentially, it's actually just conditional probability that shows that those two have an association there. So if you use conditional probability and you condition on this value, you can break up the math to find out that you actually have, now you have an association between this, and it wasn't there to begin with. And so that's kind of what we were able to do, is just basically go through that math, proving that. But that's real short of how that works.
Very good. Let's thank our speaker.